All right, welcome to lecture number 5 of game theory. So today we're going to resume our discussion about the stable matching problem. We'll talk about the Galil-Shapley algorithm, and we'll start to analyze it in some depth to see how well it works, what it tells us about the stable matching problem in general, and learn some techniques along the way that we can use to reason about this stuff. By the way, I'll often do this throughout this class, but I just wanted to make a mention of this name. So the name Shapley is sort of a famous name in game theory. Galil's claim to fame, as far as I'm aware, is the Galil-Shapley algorithm. So I don't know what else Galil did. I don't even know who Galil was, really, outside of this algorithm. But Shapley is the name of a British economist named Lloyd Shapley. And, I'll often kind of give you the credentials of the people that are responsible for the things you're going through in this class. And Lloyd Shapley, he did a lot of work in a lot of different areas relating to game theory, particularly in cooperative game theory that we'll learn about kind of soon. But Lloyd Shapley won the Nobel Prize in economics in 2012. And so, that's always kind of a near and dear to me, like the fact that he won the Nobel Prize then, because this is right around the time that I was first learning about this kind of algorithm and about Shapley in general. All right, so even relatively straightforward looking algorithms can launch careers that lead to Nobel Prizes in the end. So you're in good company in this area. All right, so we'll talk about the Galil-Shapley algorithm that we introduced kind of quickly last time. We'll reintroduce it now, talk about how it works, talk about what it does, talk about what it tells us, and then wrap up the talk about matchings. All right, so last time we kind of closed with the Galil-Shapley algorithm, but the last kind of fundamental thing we did was we looked at the roommates problem. And so just to quickly recap what the roommate problem told us, the roommate problem says you've got a group of people, an even number of people, and you want to partition them off into pairs. And the wrinkle here is that everybody cares about who they're paired with. And so we encode who they're paired with in a matrix like this. So person A likes B first, then C, then D. Person B likes C first, then A, then D, and so on. Okay, so we have every individual has preferences about who they're paired with, and we need to pair everybody off. And one of the questions we could ask is there any way of pairing everybody off that is stable? And what does stable mean? Well, we defined stable semi-formally last time, but stable means that if you go around to everybody and ask, is there someone else you'd rather be paired with, that when that person gives you their list of people that they'd rather be paired with, and then you go ask those people wouldn't leave their current match for the unsatisfied person. So there can be unsatisfied people in a stable matching, but there can't be any unsatisfied pairs, right? There's no way that there's two people who are matched with someone else would prefer to be with each other in a stable matching. Okay, so the question is, in the roommates problem, are there stable matchings? And it turns out that there aren't, right? I should say there need not be in the roommates problem. And we worked through this in the last video, so I'm not going to bore you with it right now, but basically what we did is we said, we looked at all three of the possible pairings, and we deduced that each one of them is not stable. So if you look at this pairing, there's somebody in this group who wants to be with somebody in this group, and the person in the right group that also wants to jump in with the person in the left group, right? So there's always someone who is in a pair who is willing to break their pair to be with somebody else, and it happens that those can line up. And so the outcome here is that in the roommates problem, right, if we don't have the bipartite kind of structure of the marriage problem or the other stable matching problem that we were looking at before, in the roommates problem, it's possible that you can define preferences in such a way that there are no stable matchings, right? So in this instance, for example, stable matchings don't exist. And so that means that there's no general guarantee that stable matchings exist in the roommates problem. And so then we asked, does this result, this negative result, this result of non-existence or non-guaranteed existence, does this carry over to the marriage problem? And on the one hand, it almost feels like it would have to, right? Because in the roommates problem, you don't have this rule that that everybody lines up on one side or the other and then forms pairings. So in some sense, this is a more general problem. The roommates problem is a more general problem, and it's simpler, right? It's less constrained because anybody can match with anybody. You don't have a specific, you're either on this side or on this side, and matches can only go across. And so it kind of feels like this could be bad news for the bipartite matching problem, where you have people on one side or the other. And we kind of left it at that, right? I think I might have slipped and told you the actual answer, told you whether or not it applies. But we just left it at this. And then we went there to give the Galil-Shapley algorithm. So the Galil-Shapley algorithm, now returning to the bipartite matching problem. And so whenever I say bipartite, what I'm saying is that you have a matching problem where there's people on one side and people on the other side, and the only pairings that are allowed have to cross the dotted line in the middle. And that this is called a bipartite matching problem. Bipartite matching. And just a reminder of where we've come. This problem was kind of defined, or at least the stable matching problem was defined in the 1950s in England. And they thought, oh, what's an example of bipartite that everybody can get on board with? Oh, it's marriage, right? Hetero marriage. And so nowadays this feels like an anachronism because marriage isn't defined anymore as a bipartite matching. But we'll throw a bone to the 1950s and just carry on the tradition for the time being in terms of how we describe the problem. But understand that we're not talking about men and women. We're talking about things like applicants to medical residency programs and teaching hospitals. Or we're talking about things like Uber drivers and Uber riders. Okay, so we're talking about some kind of a scenario where you have people on one side, people on the other, and a pairing can only be defined as a cross here, right? It wouldn't make any sense to pair an Uber driver with another Uber driver, right? That's just a nonsensical idea. And additionally, everybody cares who they're matched with, right? Everybody on the left cares who they match with on the right, and vice versa, okay? And there's sort of this distinction between the right and the left. So how does the Galil-Shapley algorithm work? Well, let me just refresh real quickly so that we kind of are primed for the discussion moving forward. So it proceeds in stages, being an algorithm. And the way it works is you choose one side to be the proposing side and the other side to be the tie-breaking side. And so for our purposes here, 1950s, we're going to have the men be the proposing side and the women are going to be the tie-breaking side. So what happens is each of the people on the proposing side, each of the people on the proposing side, in stage one, they go to the top of their list and they submit a proposal to the person on the top of their list. Well, if any woman receives more than one proposal, or I should say, if any proposee receives more than one proposal, then what that proposee does is select their favorite from that menu of proposals that they received. So they select their favorite and they say, I'm tentatively going to stick with you. So we'll call that the waiting list. So the woman selects her favorite among the proposals she has received, puts that on the waiting list and says, tentatively, I'm going to be with you. We'll hang out until someone better comes along. And then of the other proposals that she receives, she goes to them and says, leave me alone and never talk to me again. Right? Go back to the pool and don't come back. Right? So she says, I don't know who I'm going to match with, but it ain't going to be you. And then in the second stage, it proceeds almost identically to the first, but now we maybe have fewer proposals, right? So each of the men that's rejected in the first stage or I should say in the previous stage, now goes down their list, goes to the next person on their list, submits a new proposal, and says, "Hey, how about now?" And if that proposal is accepted, then he's tentatively with that person. Nothing's final until the end of the algorithm, but he's tentatively with that person. And if he's rejected, he goes back into the pool, and then in the next stage moves down his list. Okay, so we walked through several runs of this algorithm last time. So if you need a refresher on exactly how this works, feel free to take a look at those. But we now have some questions that we can ask. Now, understanding how the algorithm works. Oh, and I guess before I do this, I need to make sure that I mention the termination condition. So our termination condition is that we have a stage, or we have a round where proposals are made, but then no man is rejected. Okay, so that's what termination means. So as soon as we have a stage where there are no rejections, then we're done, right? And we call that a terminated algorithm. So let's ask some questions, and some of these questions are going to be very, very algorithms focused, right? So they're like the standard questions we ask about algorithms. Does it terminate? How long does it take? Things like that. And some of the questions are going to be more social systems oriented. So they're going to be more oriented towards what does the algorithm tell us now about the stable matching problem. So this is, by the way, considered one of the most beautiful kind of algorithms in computer science, partly because of what it tells us, right? So the algorithm itself is nice. It solves a real problem that is, people care about in the real world. But it also actually tells us, like the facts about the algorithm tell us something really important about the problem itself. And the story that the algorithm tells about the problem is actually surprisingly comprehensive. So it answers most of the questions that we care about in the stable matching problem. All right, so here's some questions, right? And some of these questions are about the Galil-Shapley algorithm, and some of them are about the matching problem. So for example, the first one here is not a question about the Galil-Shapley algorithm. It's a question about the stable marriage problem or the stable matching problem. Are we guaranteed to be able to find a stable matching, right? That's still an open question as far as anybody's here is concerned. And it's also not a question about the algorithm. So it seems maybe odd at first to be including that in a list of questions about the algorithm, but let's proceed and just see where it takes us. So now we have some algorithms questions. First is a termination question, right? First, do we have a guarantee that the Galil-Shapley algorithm is an algorithm, right? Does it terminate, or is there a possibility that it will loop forever? So if you've taken one of the CS theory classes, then this is a halting question, right? Do we have some kind of a halting guarantee for Galil-Shapley? So suppose the Galil-Shapley algorithm terminates. Does it find something good, right? Is what it finds a stable matching, right? That's an open question, and it is not at all. The answer to that is not at all obvious. If it's obvious to you, please come and talk to me. I want to hire you as a research assistant. And then how long does it take? And then we can ask some other questions as well. For example, not just does it terminate at a stable matching, but now suppose it terminates at a stable matching. How good is that matching, right? Are there other matchings that it could have found? Questions like that. So I'm going to give answers to these questions totally out of order, kind of in a logical order rather than in order of these questions. And I'll give the answers in the form of theorems. So these aren't named theorems, right? There's probably a Galil-Shapley theorem somewhere that just lists all of these as bullet points. But I'm going to include these as theorems just for the sake of calling them out individually, because the proofs for these things they all work on an individualized basis. All right, here's our theorem. Theorem number one. Theorem number one answers this question. The Galil-Shapley algorithm always terminates. Okay. Moreover, right, and this is actually, this feels obvious. Maybe this is obvious, right? If this is obvious, it doesn't get you a free, hiring in my lab. But it also always terminates at a matching, right? So it doesn't run forever, and when it stops, the thing it outputs is a valid matching. All right. It doesn't say anything about stability, but at least it's a valid matching. So it always terminates at a matching. All right, so let's just think about how we would show this, or how we would reason through this. And this, by the way, this approach to reasoning about why the algorithm terminates is somewhat generalizable, right? So any computer science person needs to know how to think through the answer to a question, does my algorithm terminate? And here's one way to think through this question, right? Now applied directly to the Galil-Shapley algorithm. So we'll make some statements just kind of to level the playing field, make sure that we know what we're talking about. We're going to assume that the number of people on the left and the number of people on the right is the same, right? So if I have n men and n women, m women, n and m equal the same number, right? And this is without loss of generality. We can easily extend the Galil-Shapley algorithm to a scenario where there are different numbers, and you'll do that in the homework, and the homework question explains how to do it, right? It's that easy. And then we'll analyze the case where the men are proposing to the women, though it need not be the case, right? There's no difference between men and women in the Galil-Shapley algorithm, other than we call one of them the proposing side and the other one the proposee side. So this is just the version of the algorithm that we're going to be looking through. So let's think about what it means for the algorithm to terminate. Okay, so first, let's think about why the algorithm would terminate. Okay, so here's a very simple kind of sentence that tells us why the algorithm terminates. Okay, so we know that in every round, someone proposes. Okay, that's the definition of a round. Okay, by the way, if we have a round where no one proposes, the only way that can happen is if no one was rejected in the previous round, which means that the algorithm terminated, right? So if our termination condition has not yet been met, then we know that there's at least one person proposing, okay? So what happens when someone proposes? Well, they go down to the next person on their list, right? Everybody has a ranked list, right? So here's my list of people. So if I have a chance to propose, what am I going to do? I'm going to move down. And remember, one of the ways the algorithm works is that after I've been rejected, I never go to that person again. Okay? So after I leave this, I know that the only thing that's going to happen is I'm going to go down. Okay, so what do we have? Well, in each round, there's at least one proposal submitted. No one ever proposes to the same person twice. Right? So after I've been rejected from somebody, I never go back to them. And so that means that there's only a finite number of proposals that can be submitted, right? So we have a list of n men, right? So there's 1, 2, all the way up to n. And how many preferences does each of these men have? Well, he has exactly n. Okay, so there's, the preference list of person 1 has exactly n people in it. The preference list of person 2 has exactly n people in it, and so on. And so that and each one of those corresponds to possibly kind of in worst case one round of the algorithm. So there can't possibly be more rounds of the algorithm than there are things, right? Elements in the total preference lists of the men. Okay. So notice here, I didn't reference the termination condition, right? So sometimes when you say the algorithm has to terminate, your gut reaction is going to be go look at the termination condition and somehow prove that that thing has to happen. But here I didn't actually do that. I said, I'm going to prove that the algorithm terminates by saying, here's a thing that has to happen at least once every single round of the algorithm, right? Has to happen at least once. And there are only finitely many of those things that can happen, right? I have at most n squared things on the men's preference list, and each one of those, I could have as few as one of those happen per round, but I have to have at least one per round. So that means there can't be more than n squared rounds, right? And there we're done, right? So we terminate, right? Without referencing the termination condition. All we do is say, there's a thing that has to happen every round, and there's only finitely many of those things that can happen. So we terminate. So now let's think about how we would argue that when the algorithm terminates, it terminates at a matching. Well, so let's think about let's think about what it would mean to terminate at not a matching. Okay, so suppose the algorithm terminates and what it outputs is not a matching, well, that means that somebody is unmatched. Okay, because a matching means everybody on the left has exactly one connection to one person on the right. Okay, and vice versa, right? No person on the right is connected to more than one person on the left. So if one person is unmatched, then that means that in particular it means one woman is unmatched. And if one woman is unmatched, then that means there has to be at least one woman who has more than one match, right? Who is sitting on more than one proposal. Okay, so let's think about this. So let's just play a thought experiment, and this is called a contradiction proof for those of you who are into proof. And there's some videos from my discrete math thing on Canvas that you can look at for that. But this is called a contradiction proof, which just means we're going to have a thought experiment that says, hey, suppose this thing isn't true. Now let's try to use that idea that this isn't true and derive some nonsense. So let's assume for contradiction that somebody's unmatched after the algorithm terminates. Well, then in particular, that means one of the women is left out. And we said up here that if one of the women is left out, then that means some other woman has at least two proposals. What does it mean if a woman has two proposals? Well, it means she hasn't rejected one of them yet. Right? It means that the algorithm hasn't terminated yet, right? Because part of the algorithm is that if a woman has two proposals, she rejects one, and then a new round starts, and that man goes and makes a proposal. So what we have here is that if the algorithm terminates at something that's not a matching, then the algorithm has not terminated, right? Which is a nonsense statement, right? If what I just said is, if the algorithm terminates, then it has not terminated, right? Which is a nonsensical statement. It's a contradiction, which means that that the original thing I was assuming must not be true, right? And you could also think of this in terms of a contrapositive argument. So you could say, we just showed that if someone is unmatched, then the algorithm has not terminated. And what's the contrapositive of that? Well, it's that if the algorithm has terminated, then no one is left out. Okay, so what do we have? Well, we have a full proof of Theorem 1, is that the Galil-Shapley algorithm is guaranteed to terminate in a finite number of steps. That's what this thing said, that little argument there. And when it terminates at a matching. Okay, so there we go. So now we have a check mark here, right? So now we know that the Galil-Shapley algorithm will always terminate at a matching. Okay, so this is good. This is good basic algorithmic stuff. So now let's get into the trickier questions. Okay, and so the next question we're going to ask is, how good is the matching, or what kind of matching does it terminate at? And here's the kind of the major theorem, and this says the Galil-Shapley algorithm will always terminate at a stable matching. Okay, so let's think about why that would be the case, and let me walk you through kind of a reasoning about why it is the case that when the Galil-Shapley algorithm terminates, which we know it will, the matching that it terminates at is stable. Okay, so we'll do the same assumptions we did before. It's a highly valuable exercise to take the proof that I show you now and extend it to the case where these assumptions are not satisfied. I'm not going to test you on that, but please do, and you'll also explore it in your homework. It's always, if you want to get good at this stuff, it's always valuable to say, all right, what if these assumptions fail? Then what happens to my theorem, right? And I'm telling you that the theorem result still goes through. Okay. All right, so let's think about what happens as the algorithm proceeds. Okay, so one of the things that is not totally obvious at first, but it becomes pretty clear once you think about it, is that as the algorithm proceeds, the people that are matched, or I should say specifically look at the women, the people that a woman is matched with just get better and better, right? They never decrease. Okay, so if a woman ever rejects a proposal, the only reason she would reject that proposal is if it improves the person that she's with, right? If it's better than the last person she was connected to. Okay, so in the Galil-Shapley algorithm, the longer the algorithm runs, the better things look for each of the women. Okay. So now let's think about how we can use that observation to prove theorem 2. Okay. So let's look at a particular match. And let's say, okay, suppose the Galil-Shapley algorithm runs and it churns and churns and churns, and then it terminates at a matching, and here's the matching. So the matching is here's just a zoomed in on 2 pairs in the matching. There's other people in the matching as well. But let's look at these 2 pairs, and let's argue that at least here, with these 4 people, the matching is stable. Okay? And then we'll use that argument that the matching is stable among these 4 to say, therefore, it must be stable for any 4, and therefore for everybody. Okay, so let's just imagine, for the sake of argument here, that we've got these 4, and the white lines correspond to the output of the algorithm. So the white lines are the Galil-Shapley algorithm output. Okay, so that's the white lines. But suppose that Mr. Y, right, this guy down here, who's matched to Ms. Y, suppose that he's unhappy with his match, right? In the sense that he wishes he had been matched with Ms. X. Okay, so that's what that blue dotted line means. It means that Mr. Y, he's matched to someone, but he wishes he had been matched to Ms. X. So what does that mean? Well, just mechanically, that means that if I took Mr. Y's preferences and I wrote them down, they would look like this. So let me write down Mr. Y's preferences. Mr. Y prefs. So we don't know, who else he has preferences over, so I'm going to put some dots in, but, he's got some favorites. And then somewhere along the line, he finds Ms. X. And then there's some more, and then somewhere along the line we find Ms. Y, and then there's some more. Okay, so this is what we know about Mr. Y's preferences. Okay, so Mr. Y thinks X is better than Y. Okay, that's all we know. Well, in the Galil-Shapley algorithm, remember the white lines here, the matching here, is the output of the Galil-Shapley algorithm. So in the Galil-Shapley algorithm, what does it mean if somebody is matched, if a man is matched to a person that's low down in their list? Well, that specifically means that somehow he would have had to propose to everybody on the list all the way down to that person. Okay? So the fact that he is currently matched here means that at some point he proposed to Ms. X during the course of the algorithm. And by the way, if you're reading along with the notes, this argument is essentially repeated in a bunch of text down below this box, right? But I don't want to distract you with a bunch of text when I can be pointing at the picture here. Okay, so what do we know? The fact that he is matched at Ms. Y means that at some point along the line, he had proposed to Ms. X. Because every time a man proposes, it's to someone lower down on his list. Okay, so he has proposed to Ms. X at some point. So Mr. Y proposed to Ms. X at some point. All right, so that's fine. So why isn't he connected? Why isn't he matched in the output to Ms. X? Well, that's really simple. It's because Ms. X rejected him. Okay, so what does that mean? It means that somehow someone came along that Ms. X liked better than Mr. Y. It could have been Mr. X, right? It also could have been somebody else, right? But we know that Ms. X rejected Mr. Y's proposal. Okay, what does that mean? Well, not quite sure, but if we follow the algorithm a few more steps, now we know that in the end, Ms. X is matched with Mr. X, and so that means that whoever it was that Ms. X rejected Y's proposal for, she liked that one better than Y, and then she liked Mr. X better than that one, right? So we know that Ms. X likes Mr. X more than she likes Mr. Y. So what can we do? We can actually write down what we know about Ms. X's preferences. So here's Ms. X prefs. Well, she's got some favorites. We don't know who they are. And then she likes X, and then she likes some more guys, and then she likes Y. Okay. So what does this mean? It means that Ms. X prefers the person she is with over Mr. Y. Okay. So we know that X, I should write Ms. just to be precise. Ms. X prefers Mr. X over Mr. Y. Okay. So what does that tell us? Well, it tells us that Mr. Y can't get out of his match, right? Mr. Y is not going to be able to convince Ms. X to join him, which means that if you want to kind of narrow stability down to just these four are stable. Okay, Mr. Y, the fact that Mr. Y is not matched with Ms. X means that she won't take him. Okay, that's it, right? Either he didn't ask in the first place because he doesn't like her that much, or he did ask and she rejected him. In either case, she won't take him. And now here's the surprising thing, is that argument that these four are stable actually extends to the entire thing, right? How do we know? Well, because these Mr. X, Ms. Y, whatever, these were arbitrary names. So we zeroed in on four people and said, hey, suppose one of these four is unhappy, then what does that tell us? Well, that tells us that it tells us that the whole thing is stable, right? Since these four are stable and these four are arbitrary, then the whole thing is stable. So therefore we're done, right? That actually completes the proof that the Galil-Shapley algorithm terminates at a stable matching. Okay, and that's that fact. So what does that tell us? Well, the Galil-Shapley algorithm is an algorithm, which means that if you put in an input, it gives you an output. So now what we just said is that if you give it any preference rankings, right, any list of preferences, then it will spit out a stable matching for those preferences. Well, that's remarkable. That means that every single possible input has a stable matching. And so that actually answers two questions for the price of one. So, obviously it answers this one that says yes, it gives us a stable matching. But the fact that it gives us a stable matching tells us an answer to this one. Tells us that every single possible set of preference rankings corresponds, or I should say has at least one stable matching. So, way to go, Galil-Shapley. This is looking good. So now let's ask kind of a slightly more mundane algorithmic question, like how long does it take? Well, let's do this. The Galil-Shapley algorithm terminates in at most, in fact, fewer than n squared minus n plus 2 stages. Okay, and we'll talk about what that means in just a moment. But let's think about why that's the case. In a stage. A stage is not a terminal stage if someone got rejected. So each man can get rejected at most n minus 1 times, right? And that's because his last, if he gets rejected n minus 1 times, then that means there's only one person left to propose to, so that by definition has to be his last proposal. So a man can only get rejected n minus 1 times. If you're in a non-terminal stage, there has to be at least one rejection. And so, in the end, every woman has to get a proposal, so there better be at least one rejection. And so that means that we have for our first stage, or our first proposals, there's one stage. So everybody submits a proposal the first time. And then what happens if the worst possible, if this is just fine-tuned so that you get exactly one rejection every time, and everybody has to submit their full number of rejections, well, then that means that each man could be rejected up to n minus 1 times. So you've got n men, n minus 1 rejections. And so in total, there's this many extra stages. And then the last proposal's a stage. So that the terminal stage has proposals but no rejections. So that they weren't counted in the first. So what's the total number of stages in this kind of worst case? Well, just do the math, right? One for the first stage, one for the last stage, one for these intermediate stages, and you end up with n squared minus n plus 2. Okay, so there you go. That's the number of the largest possible number of stages you could have. And so, you know, this all just comes from the fact that, you know, everybody's preference list is finite, right? So, you know, there's some extra details. If you look very closely, you know, you actually can't do this. You can't quite hit that worst case upper bound. So the worst thing that could actually happen is this. I'm not going to go through the details that kind of get us there, but let's think about what this means. So I'm going to make a claim that's going to feel wrong, and then I'll explain why it's actually right. My claim is that the Galil-Shapley algorithm is a linear time algorithm. Okay, so here's my claim. Galil-Shapley algorithm has big theta of n. Here, I'm going to use a capital N. Complexity. Why did I use a capital N? Because the size of the input of the Galil-Shapley algorithm is not the same as the little n. Okay, so let's think about what time complexity means. And so most of you hopefully have had algorithms. If you haven't, go take algorithms. You know, you owe it to yourself to have taken that class at some point before you graduate. And I'm specifically speaking to people in security programs that aren't required to take it. But when we talk about time complexity, we talk about how the running time of an algorithm scales with the size of its input. Okay, so we usually state that in terms of n, but here n means something different. So the little n, right, this little n here, means something other than the size of the input. Right? This little n is the number of matches, okay, which is really the size of the output. Right? It's not the size of the input. What's the size of the input? Well, the size of the input is actually 2n squared. Okay, so the input size is 2n squared. So why is that? Well, it's because if you take all the men's preferences, right, there's n of them, n men, and each man has n preferences. So you can collect the preferences of the men in an n by n grid. Okay, so the men's preferences, the full preference rankings, take up n squared space. Okay, so men's prefs, n squared space. Right, the size of the men's preference list in total is n squared, and the women's preferences is the same, n squared space. Whoops. There we go. Oof. There we go. So the women's preference is n squared space. So the total input size is this 2n squared, 2 little n squared. And so what did we say? Well, we said that the running time of the algorithm is at worst, it's n squared. So the running time is proportional to the input size, right? Directly proportional to the input size. And that means that this is a linear time algorithm, right? If you double the input size, then you double the running time of the algorithm in worst case. Okay. And so what does linear time algorithm mean, right? If we go back down here and we look at this big theta of n, right? It's always worth thinking about what linear time means for algorithms. Well, it means, and you could have reasoned through this without actually doing the math, just looking at how the Galil-Shapley algorithm works. But linear time means that you never have to look at any element of the input more than a constant number of times. And in this case, you never have to look at any element of the input more than once, right? Each entry in the preference list only gets referenced once. And the fact that it's linear time, it's big theta of n, not big O of n, that means that it could be referenced exactly once, right? It could be that you have to look at the entire input. You can never make some kind of guarantee that like some portion of the input gets thrown away, right? So you can look at every element of the input, but you never have to look at any element of the input more than once. Okay? That's what linear time algorithm means. So that's incredibly powerful, right? To have an algorithm that takes this really challenging combinatorial problem, find a specific needle in a combinatorially large haystack, and do that now in linear time. Now that is a remarkable feat for this algorithm. So it's easy to say oh, all you did was just a quick complexity analysis. It's easy to miss how remarkable that complexity is. But it turns out that we actually have a very strong complexity result for this algorithm. So those are those 4 questions, right? Those have now been answered. So what else is there? Well, let's think a little bit about how good the matchings are. Okay, so we're going to ask a question now about quality. So we know that the matchings that the algorithm outputs are stable, but are they good? Okay, so let's take a look. Let's take a look at an example, and then the kind of the specific questions we're going to be asking here have to do with favorite, right? So we haven't yet looked at an example where there's more than one stable matching, but here's one, and because it turns out that you could have multiple stable matchings in one of these problems. And so suppose you had multiple stable matchings, then the question remains, how do you rank them, or can they even be ranked, right? Can the matchings themselves be ranked, and how does the Galil-Shapley algorithm kind of relate with that? So here's a set of preference rankings. I encourage you to pause right now and go run the Galil-Shapley algorithm first with the men proposing, second with the women proposing, right? So run the Galil-Shapley algorithm twice, and then see, compare the 2 outputs you get. And see what they look like. Okay, so everybody pause the video and run Galil-Shapley on this, and then come back. So for those of you who didn't pause the video, there are the rankings, or the matchings that you get when the men propose versus the women propose. Okay, and so the specifics here aren't too important, but you can take a look and see. See that, suppose we're looking here at where the men are proposing, A gets matched to A, D gets matched to B, B gets matched to C, and so on. And the numbers here correspond to how happy that individual is, right? So the 1 here means that little b got his first choice, right? So you can reference that up to here and say, well, little b's first choice is C, the big C. And so, sure enough, little b got matched with C, and that's his first choice. Okay. And so, if you look at the one where the men proposed, you see a bunch of low numbers down here, which means that, all the men got at least their second choice. And you see a bunch of high numbers here, right? So that's intriguing. So the high numbers mean that the women kind of fared badly in the matching where the men proposed. So now let's look at the one where the women proposed. Now, where the women proposed, all of the women got at least their second choice, right? And 2 of them got their first choice. But most of the men got their third or worse. One of them actually got their fourth, and one of them got lucky enough to get his second choice. Okay, so that's intriguing, right? That now there seems to be some kind of favor that is given to the proposing side, right? So when men proposed, the men did well. When the women proposed, the women did well. Okay, so it turns out that there's at least one more stable matching for this particular preference ranking, and it looks like this. And notice that it's not like particularly good for either side. So this is just some other stable matching that the Galil-Shapley algorithm did not output. That's sort of mediocre for everybody. Mediocre for all. Okay. So what do we see here? Well, it looks like men did well when they proposed, women did well when they proposed, and then there's this other one that we don't know anything about. So let's actually be exhaustive about this and ask each individual which matching they like the best, and we can create this little table. And so we can say, let's look at this matching, and then say, what did each of the individuals, like which preference ranking did each of the individuals get? Well, all the women got their third choice in this ranking. The men got second, first, and second. In the matching where the women proposed, the women got first, second, first, and the men got third, second, third, fourth, and so on. And so let's go and ask an individual which is their favorite ranking or favorite matching. So if I go and ask the Mr. D right here, his favorite matching is the one that he got when he proposed, and then all the other ones are worse. Okay. So if I go and ask Mr. C, his favorite is the one where he proposed, and all the other ones are worse. B, his favorite is the one where he proposed, and all the other ones are worse. And then A, it's the one where he proposed, and none of the other ones are better, right? So I'll rephrase it very slightly there, just to make sure that you see this is a weak preference. So he was just as well off in this other random matching, this stable matching, than he was in his own, in the one where he proposed. So we can do the same thing with the women, and we won't do this with everybody, but let's take a look at the women. So this woman, Ms. A, she's best off when the women proposed. B is best off when the women proposed, right? And the same as when we got that other stable matching, but she's best off when the women proposed. C is best off when the women proposed. D is best off when the women proposed. Okay, so if I went and asked each of these individuals, which is your favorite stable matching, right? And I actually give them a menu of stable matchings, then each individual will say, my favorite stable matching gave me the same match that I got when I proposed. Okay, and this turns out to be general. This turns out to be generally true. When you run the Galil-Shapley algorithm with the men proposing, the matching that it produces is the one that any of those men would choose, right? Out of all of the possible stable matchings. Even if there's 1 million stable matchings in that particular system, the men are happy with, they're happiest with the one when they propose, okay? So this is also kind of remarkable. There could be, in a population of thousands of people, there could be thousands of stable matchings. And the Galil-Shapley algorithm somehow cleverly picks the one that is best for the proposing side in a very strong way. Okay, so we can define a stable matching as optimal. So we can call it optimal for a person if that person is at least as well off with that stable matching as under any other stable matching. So if I say a stable matching is optimal, here in this particular case, what I mean by optimality is I mean that it's best for a particular person out of all the stable matchings. I'm not saying it's best out of all the possible matchings, right? Only best out of all the stable matchings. And the optimality theorem for the Galil-Shapley algorithm says that for any input, that when the men propose, that the output of the Galil-Shapley algorithm, so here we are when the men propose, the output of the Galil-Shapley algorithm is optimal for each man, okay? And I don't mean optimal for the men in general, right, which would be a weaker statement. That would kind of lead you to think that maybe some men are really well off and some, have to give something up in order to be, in this stable matching. No, I mean that out of all the possible stable matchings, if I went and I asked each individual man, are you happy with this one? They would say yes. I wouldn't choose another stable matching over the one that I got here. Okay, and then the same, of course, is true for the women, right? If the women propose, they get, then each one of them is satisfied with the output of that matching. And so then, one final question we can ask is, what if you run the Galil-Shapley algorithm with men proposing, and then you also run it with women proposing, and you get the same answer, right? What does that tell you? Well, it turns out that tells you that there's only one matching. There's only one stable matching. Okay, so the optimality theorem says that, in a very strong sense, the proposing side gets the best thing for them, and then the uniqueness theorem takes that and says that if everybody has strict preferences, so we've got no people who kind of are ambivalent about who they get matched with. If you run the Galil-Shapley algorithm twice, so you run it once with the men proposing and then once with the women proposing, and you get the same answer, then that one stable matching is the only possible stable matching in that for those preferences. Okay, so I'll just highlight the specific bits of the statement here. So if the matching system obtained by the Galil-Shapley algorithm when the men propose is identical to, come on, there it is identical to the matching that's obtained by the Galil-Shapley algorithm when the women propose, then that matching is the unique stable matching, right? And in math, when we say unique, we mean it's the only one that satisfies the particular things that we're trying to satisfy. So if we look at the preferences from Monday, from the previous video, that's what these are depicting here. We ran the Galil-Shapley algorithm twice on this, just as an example of how to run the Galil-Shapley algorithm. The first one we ran, with the men proposing. The second one we ran with the women proposing, and we came up with exactly the same output in either case. And so then if I came to you, and you'll see this on the homework, if I came to you and said, "Are there other stable matchings for these preferences?" the answer is no. And you would know this because of this uniqueness result that says if you run it with the men proposing, or I should say the men proposing, and then you run it with the women proposing, and those two runs land on exactly the same matching, then that's the only matching, the only stable matching there is. Okay. And so one of the nice things here is that if you're looking for all stable matchings, right, if you're interested in understanding whether there are more, this can be a certificate that there are not more, right, that there's only one. Now, if you run the Galil-Shapley algorithm twice, once from one direction, once from the other direction, and you get two different answers, then that doesn't tell you anything, right? All that tells you is that there's more than one, and there could be many, many more. That's right. It's possible for many other matchings to be to exist. So this is probably the weakest of the results that we have here in this problem, but it's one of them. So this is the end of the line for the stable matching problem. You can always refer to the notes, the printed notes, for some more examples and for a little bit more explanation about how this stuff works. But I love the Galil-Shapley algorithm because it's a relatively simple algorithm to understand. And it's actually used to match medical students with graduating medical students with residency programs, and it's used in some other contexts as well. There's an example in the notes about using it for load balancing in certain kinds of distributed systems and cloud systems, and it's this kind of magical thing that as soon as I can show you like the right answers for the Galil-Shapley algorithm, then it gives you this basically complete characterization of a bunch of valuable things to know about the stable matching problem. And so next week we're going to start thinking about cost sharing. And so when we start thinking about cost sharing, we're going to be introducing concepts of value and concepts of utility. Notice that we've got no notion of utility here at all yet. Right? There's no subjective kind of numerical value that we put on anything. We're still only thinking about value in terms of where the person that I match with lands in your preference ranking. But very soon we're going to start thinking about what if I have a preference ranking, but I also think that the people on the top of the list are twice as good as the people on the bottom of the list, and I start thinking about how do the numbers actually end up working out there. And that will open up a whole new realm of interesting questions.